All right, well, welcome to the webinar. We've got a pretty good group here today. I think we may see a few more trickle in as we begin the webinar. But let me go ahead and make a few introductory comments to kind of let you know what this is all about and what to expect. This is for new users for Design Expert. The idea is to introduce design of experiment concepts and also to introduce StatEase Design Expert software for the creation and analysis of multiple types of experiments. By way of personal introduction, my name is Richard Williams, and I've been a StatEase consultant for a little bit over 4 years now. But prior to that, I spent 38 years in the chemical industry in roles focused on product and process development and improvement. By training, I'm a chemical engineer with a business degree, and I'm also a Six Sigma Master Black Belt. In my experience, I feel that DOE has been underutilized for problem solving and process optimization. But equally, I think DOE should be the tool of choice to help us launch reliable products and processes from the very start. This is the idea behind quality by design, or design for Six Sigma. Over the past 10 years or so, I focused on providing training for product and process improvement tools. So today I'm very happy to provide this webinar to get you started with design of experiments. Warning, however, we will spend 1 hour together, and this is a huge topic, right? So I'm obviously not going to be able to cover every detail. But my goal is to give you enough of a flavor so you understand where DOE would fit in and why you would want to use it. I hope that I will give you enough insight that you could begin to use design of experiments and Design Expert in particular, but it's a big topic. So along the way, we'll also offer you resources to continue your DOE journey as well. Okay. So making the most of this 1 hour that we have together to prevent audio disruptions, I have all the attendees muted. But during the webinar, if you have questions, these will be monitored in the question box in the GoToWebinar dialog box. And Sherry Kraber is on the line, and she will be happy to answer those questions as best as we can during a 1 hour event. But follow up, you can always send questions to stathelp@statease.com for additional questions that might be a little bit more elaborate or beyond what we can handle during the webinar itself. Also, the slides that I'll be using and this recording will be posted on the StatEase webinars page within a few business days. Okay, so we're going to have every opportunity for you to capitalize on this 1 hour investment of your time. Okay, so the goals really, we want to help you understand why you would want to consider using DOE methods. We will introduce Design Expert by demonstration. We're actually going to go through 3 example problems today from start to finish, which admittedly is quite a challenge to get in a 1 hour time block. But I really want to expose you to the modern DOE tools that exist. And perhaps some of you are familiar with some of the approaches that historically had been used, but the science has advanced, and I want to make sure that you are aware of the skills and the tools that are available. So the next steps, please raise your hand in the GoToWebinar button, just kind of a check to see if it's all working out and you're able to hear and everything's working out for you. If I could ask you to do that for me. There, I see a couple of hands. Okay, super. So that must mean the voice is coming through and you can see my screen. So if that becomes an issue, please feel free to, in the chat window or the questions box, just let me know if there's something I need to address. Okay, but if not, let's continue. So the agenda, in brief, I've kind of mentioned it already, but the idea here is DOE, what's in it for me? Why do we even want to consider using this type of an approach as opposed to some other experimental approach that we could think about? We will then get into a factorial design, characterizing the main effects and interactions in a system. Okay, so this really is kind of where DOE began, a century ago, uh, really trying to understand what factors impact a process with as little work as possible. But it goes on from there, and we'll learn how to optimize using response surface methods. And then we're going to re-aim this tool set toward the specific situation for mixtures. Okay, formulation work, there are a couple of uniquenesses to them, unique twists, and we need to kind of refocus the tool set in order to work with mixtures. Okay, so that's where we're going to go. So what's in it for me? Well, so when we think about kind of the engineering approach to thinking about the world, we view things as some kind of process. Let's think about maybe making cookies in an oven, okay, a process for baking cookies. And the idea is we have some controllable factors and some property of interest, some responses, we'll call those Y's. So for cooking, I might have, cooking cookies, I might have controllable factors, might be time in the oven or temperature in the oven, or categoric factors like the oven rack that I choose to use or the type of cooking pan that I use, right? Categoric choices. So these are controllable factors. And what we want to do is study the impact of those factors on some response of interest, like the flavor of the cookie, or perhaps the yield, cookies that are not over or undercooked. Now, the problem that we have is that we always have noise in a system. We always have variation. If we try to do the same thing 10 times in a row, we will probably have 10 different answers to some extent, right? There'll be some variation in the system. So our goal is to relate the X's and the Y's, the controllable factors and the responses, despite the fact that we have some noise in the system that's trying to confuse the correlation, okay? So a design of experiment is a planned approach for determining cause and effect relationships. Okay, so rather than doing haphazard type experimentation, we are going to lay out our plan for experimentation in detail and follow a very methodical approach. Now, when we do that, we're going to benefit by doing something called multi-factor testing rather than one factor at a time, OFAT. Now, perhaps you've been of the opinion or had been taught that you have to hold everything constant and only change one factor at a time in order to understand that factor's importance. Well, that's simple and easy to understand. However, there's some shortcomings to that approach that a multi-factor approach will overcome. Multi-factor approach meaning we're actually going to intentionally change more than one thing at the same time and then rely on some math to decode the whole story and make sense of it all, okay? And the primary benefit, or one primary benefit, is that only a DOE can identify something called interactions. Well, what's that? Okay, so one factor at a time experimentation cannot identify interactions. An interaction is when the impact of one factor determines the influence of another factor, right? They're related. So in that schematic in the upper right, we're doing cookies now, and so we have the yield of the cookie, right? So we want them properly cooked. We don't want them undercooked or overcooked. So we're studying temperature on the x-axis, and the two lines represent cooking time. So the dotted line is with a short cooking time. So at low temperature with a short cooking time, we're undercooking the cookies. So our yield is low. But as we increase the temperature with a short cooking time, we end up with a situation where our yield improves because we're properly cooking more of the cookies. On the other hand, if we're going to work with a solid line with a long cook time, well, at a low temperature, we're doing just fine. But as we increase the temperature, our yield goes down because we're burning too many of the cookies, right? Too much temperature for too long. So the impact of one factor, say cooking time, depends on the set point of another factor, say temperature, right? They're linked. You cannot discover these interactions with a one factor at a time experiment. So the idea is a DOE with its multi-factor approach and its parallel processing gives us more information about the system than a one factor at a time experiment. And the statistics provide confidence in the findings, right? We're going to rely on math and statistics to give us a very strong indication of the significance of the things that we're finding, okay? So in Design Expert, we have several different design choices, several different options that are there. And we like to apply what's called the SCO strategy, the Screen, Characterize, Optimize approach, where perhaps an early round of experimentation might be to screen a system for important factors. If I'm cooking cookies, I might want to screen, just make sure that time matters and temperature matters, or maybe the type of cookie sheet or the oven rack, okay? I might also evaluate the relative humidity in my cooking environment, maybe find out that that isn't significant, or it is. But we may be able to envision many different factors that could impact the flavor of a cookie or the yield. And we might want to screen that so we are only working with the critical few. Then we may want to characterize it, find out the main effects and these interactions that we spoke about. And or we may want to optimize the system, probably using a response surface type design that we will see in the second example today. A little schematic in the upper right are the types of designs that we have. So we have factorial designs, which you'll see in our first example, response surface that you'll see in the second. And then we're going to use a special case of mixture, which will be mixture combined with a process factor in the custom designs, right? So we're going to do 3 examples quickly, okay? So the overall process for doing a DOE is not really unlike any other experimental approach, but it kind of bears a brief mention. Obviously, we want to define the objective in terms of measurable responses. We want to select the input factors to study. Design Expert will help you choose a design to use. You get to do the hard part. You have to conduct your experiment. We're going to come back in steps 5 and 6 and 7, and we are going to give you tools and techniques within the software to help you analyze your results and to interpret using graphics. We like to use graphics as much as possible. 8 as well, we're going to optimize the system, and we'll show you how that gets done. We'd like to test our predictive model using a confirmation run, right? So we've found the optimal conditions. Now we want to actually go prove that it works as advertised. And it's up to you to decide when and how to celebrate. So let's get right into it. Let's look at a factorial demonstration. We're going to characterize the vital interactions. So we're going to look in a factorial design where this is the state of the art, that began maybe a century ago, of how to, with as little work as possible, characterize a system. Okay, so here's the example that we're going to look at. We have a reactor. There's my chemical engineering coming through again. So we have a reactor system, and we've got 5 factors that we want to evaluate. And the goal is we are going to maximize the yield of this chemical reaction. Okay, so we've got feed rate, catalyst, etc. Notice that that 5th one is atmosphere. That's going to be a categoric choice, right? So it's not a number, but it's going to be nitrogen or air. So a categoric, option that we have. So we can include factors like that. So one of the things that honestly is probably the most difficult thing to grasp in this 1-hour webinar is this idea of sizing the experiment properly so that we have sufficient power to find what we're looking for, okay? So unfortunately, I'm gonna have to abbreviate this a little bit, and you may need to do a deep dive a little later on this particular topic, but let me try to give you the idea in gist. We wanna make sure that we have we're collecting sufficient data to answer the question that we have. We recognize that there is variation in the system, those noise factors that are at play, and we need to create a strong enough signal. In other words, the factors that we're studying have to give us a strong enough signal that we can see it relative to the noise in the system. So what we do is we use a concept called power in order to decide whether or not we're collecting enough data to accomplish the goal. And we have to take a decision of what the delta Y is and the sigma. So let's start with the second one, the sigma, the variability in the system to begin with. Well, if we were to go out and do the same conditions, same run 10 times in a row and calculate a standard deviation because our results varied a little bit, that would be the sigma that we're talking about, right? The variability that's inherent in the system. When you try to do the same thing multiple times and don't get exactly the same result every time, there's this natural variation, that Z that we talked about. Okay, so that's the noise. Now the signal is a little bit more of a decision that we have to take. And the idea is what we're looking for, the signal that we're looking for, the delta Y, we have to kind of make a business decision here of, well, if I'm improving the reaction yield of this system, and let's say it's running about 80%, well, what's material to us? Do I need to study that down to 0.001%? Well, no, that'd be too extreme. Do I need to study plus or minus 10%? Well, 10%'s kind of lax. I would probably want to have a little bit better read on that. So we settle on 3%. So the way to interpret that is, if my factors cause at least a 3 percentage point change in the yield, I want to find them. If it's less than that, I'm willing to forego finding them, okay? So if a factor only causes 2%, I'd reach the conclusion that it's okay to miss that because I'm really looking for something a little bit more, stronger contributor, okay? And so it's that signal to noise, the 3 to 2 that drives this thing called the power calculation, so that we make sure that we properly size the experiment, collect enough data to answer the question of interest. Okay, well, that's probably as deep as I can go on that topic for now, but let's go ahead then and begin the journey. Let me open up the right. So here we are, we're gonna start this design. This is the opening page in Design Expert, and we're going to start a new design, okay? And that brings up this regular 2-level factorial design page here. So on the left-hand side are all the different design options that we have in the software. And again, probably because of historic reasons, the most commonly used designs have been the regular 2-level factorial design. So that's kind of the default splash screen that we offer up. But there are other choices, right? There's minimum run characterized, there's optimal, there's all kinds of different choices in here, which are obviously going to be beyond the scope of a 1-hour webinar. But we will look today, we'll do an example underneath response surface, and we'll do another one underneath, well, actually custom designs, this optimal combined design. So in this type of design, the regular 2-level, we see the number of factors listed along the top edge and the resulting number of runs along the bottom edge, okay? Well, we have 5 factors, and we are gonna do what's called a full factorial. So we're gonna click on this one down here, 2 to the 5th, right? So that's 2 levels with 5 factors means 32 runs. So that's the one that we'll use in this full factorial example. Notice, and I'll come back on this later, that the one just above it with 16 runs is green, okay? The green ones may be perfectly suitable as a choice for characterizing a system, depending on the power. So we'll take a quick look at that at the end of this example. Perhaps we could get the same results with a little less work, okay? But we'll go with a full factorial. We'll click on next. And this is the input screen. So here's where we would go ahead and type the information. So the first factor would be, this is the feed rate, and it's in liters per minute. And we're going to go from, I think, 10 to 15 in this example, right? So we will go ahead and input all of those. Now I'm going to close out of this one, and I'm going to open one that's already filled in. And as soon as I find it. Okay, and now I got to move it over here. Pardon me. There we go. So here now we have one that's already filled in. We have the all of the 5 factors listed. Notice this last one has become a categoric choice as opposed to numeric, because it'll be input as either nitrogen or air. Okay. Once we input all that, we go ahead and hit next. This is where we're going to do that power calculation. And that delta Y that I said was 3. And the noise in the system was 2. So the signal to noise ratio is 3 divided by 2, or 1.5. And we click next, and we see that the power, my ability to find if factor A causes at least a 3 percentage point change in the yield, given the noise in the system of 2, we have a 98% chance of finding it. Okay, and same for the other factors. That's good power. We typically want to see at least 80, you know, depending on what we're doing, maybe go as high as 95 or so. But if we're going to do experiment, we want pretty good assurance that we're going to find what we're looking for. So here we've sized the experiment and we're satisfied with 98% power. And then we'll finish the design. All right, once we do that, so we can see our 32 runs that are listed, this is what we would go out to the lab and do. And I'll get my data. So I have a way of cheating here to get some data. I will simulate the data. This one's going to be reactor, and there, just like that, we have data. Admittedly easier to do in class than in the real world, but there it is. So once we've collected our data, we want to go underneath analysis here, and we want to analyze our data. So we get this opening screen here, and we will start the analysis. And here now, I'm going to look at this thing called a half normal plot. So let me open up that view a little bit. Now, the way this works, this is kind of an ingenious little graph, but the way this works is this. This red line is the software's estimate for the noise in the system. And each of these squares are factors or interactions. So for example, this blue square here is the impact from atmosphere, one of the factors. This one over here is a 2-factor interaction, DE, okay? Remember, you couldn't find that with a 1-factor at a time experiment. So each of these little squares is a factor or interaction term. But the ones that follow along this red line can't be distinguished from just random noise in the system. So this cluster over here, all of those I'm going to select and include in the predictive model. These are the things that appear to be statistically significant. We can confirm that by looking at the Pareto chart, and we have some statistical limits here, and we can see that we've probably made a pretty good selection, that these things that we've selected tower above the Bonferroni limit and even the t-value limit. Okay, so that's how we've picked what belongs in the model, right? Our predictive model depends on those things. Then the mathematical heart of the software is the ANOVA table. And in a full class, we would go into greater detail, but suffice it to say now that the model we've selected is statistically significant. The easiest way to see that is it says the model is, well, significant. Okay. We like p-values. We want to see p-values that are less than 0.05. And in this case, each term that we've selected is less than 0.05. Okay, so it's a good model. And the fit statistics over here on the right, we have, raw R squared of 0.96, adjusted R squared, and something called the predicted R squared which is a good indication of how well this model would predict, new information or new data. Okay, so this is a pretty good fitting model. Okay, but notice what we have here is we have B, D, and E, and two-factor interactions, B, D, and DE, and we have E is the atmosphere, so that's a categoric choice. Okay, so now we can look at the diagnostics, and here in a full course we would go through much more elaboration to describe all this. But in the upper left, we have something called the normal plot of residuals, and the idea is the residuals, the difference between your predicted and actuals. Those residuals should be normally distributed, and if they fall along this red line, it meets that test. So we're happy enough here. That looks pretty good. In the upper right, we want to look at the residuals versus predicted. And here we don't want to see a megaphone shape or points outside of the red line. If we did, that would be an indication that we would want to do something to our data called transforming it before we analyzed it. But we're good here. In the bottom left, more hints to this concept of transformation. This box Cox plot says I don't need one, it says none. So we're happy with that. We also want to look at the predicted versus actual. We want to see that this line splits the data along its range, and we're happy. So that's good. So with that, we have a robust analysis that makes good sense, good integrity. So now we can look at the model graphs. In here, Design Expert's pretty good at giving you the most relevant graph to begin with. In here, it's going to give us the BD interaction plot. Okay, so I have catalyst along the bottom. Remember, we have an interaction term. So if these two lines are not parallel, that's a hint that you have an interaction taking place. But here we have the catalyst and the two different temperatures that we studied, 180 and 140. Okay. Now remember, we want to maximize the yield of the system. So right now it looks like this point up here is a pretty good candidate. But let's see what happens if instead of nitrogen, we toggle that and we look at air. Everything goes down, right? So we still have an interaction, but we're not able to achieve as high of a yield in the system. So we're going to go ahead and go back to nitrogen. That's the better answer. These little whiskers on these lines called the LSD bars, they indicate the statistical significance. So if I click on that optimal point, I can see that these whiskers don't cross the red reference line, so that all of these other conditions are statistically inferior to the one that we've picked. And over on the left, we can see that the projected yield of the system would be 93.6 if we run at those conditions. And indeed, those are statistically different than the other options. Okay. So we were able to analyze this using a graphical approach. Okay, so let's look at the slides again. So the full factorial, right, where we tested everything in combination with everything else at its high and low level, they can characterize all the main effects and two-factor interactions, and in fact, it'll go higher than two-factor interactions. Even though 3, 4, and 5-factor interactions are extremely rare, you had the mathematical ability to calculate them and determine them if indeed they existed. Okay. We didn't see any of those, right? So all we saw was two-factor interactions. Now, power assesses the probability an experiment will identify important effects, and it's driven by that signal-to-noise ratio, and ideally we want to be between 80 and 95% with the power, so just the right amount. We don't want to go collect too much data, but we certainly want to collect enough so that we have the certainty of answering the question. Now, I mentioned that there was that green design at 16 runs that we could have thought about, right? So do half as much work. And that certainly would have allowed us to find the main effects and two-factor interactions. So that's the beauty of those green designs. but it would come at a sacrifice in power. Had we chosen that one and evaluated power, it would have been 77% power. Now that's close to 80 if you round kind of funny, but you know, it doesn't quite cross the 80, and so we'd have to make a decision. And I think that would boil down to how important was it that we didn't miss anything. If you really couldn't take the risk, then perhaps you'd want to do 32 runs. If you felt that 77 is close enough to 80, then maybe you go ahead and try with 16 runs and see how it goes. Okay. In most cases, I would probably go ahead and do the 16 runs. Okay, so that's kind of the historical factorial designs that have been around for a while. And of course, now we really want to learn how to optimize a system. So we're going to talk about response surface designs. And let me introduce it this way. On the left-hand side, we have two factors plotted along the bottom, you know, x1 and x2, and then we have this response surface, the colored thing on top. And this is the type of response surface that you can create when you have a two-factor interaction present, or an interaction term, right? 6AB up here. Well, you can introduce a twist to the response surface plane with a two-factor interaction, but what you can't do is evaluate a hill or a valley in the interior of the design space. We would need additional terms to do that. Specifically, on the right-hand side, quadratic terms might help, right? Squared terms, 6a squared and 6b squared, right? To introduce curvature along two different edges so that if you had an optimal set of conditions somewhere in the interior of the design space, you could find it. Okay, so that's why this is an optimization design instead of characterization design, where you're satisfied just finding main effects and interaction terms. So in this case, now this next study that we're going to do, we're going to look at what's called a central composite design to work with a reaction in again another chemical engineering example. But this little pictorial at the top is kind of showing you what a central composite design would look like. The factorial points are the blue points, so that is really comparable to what we just did in the last example. But in addition to that, we are going to run some center points, usually more than one, so that we have well, some interesting properties. So we really want to get a good read on what the center point is. But then we're also going to run these axial star points, okay, outside the faces of the cube. And those are going to allow us to fit quadratic terms, those squared terms, effectively. Now, sometimes people ask, well, do those axial points need to be outside the cube? And the answer is, well, they don't have to be, but we like them to be because it'll give the best design properties in the design. But if it's impractical to put them there, we give you the option to walk them back to the face or to move them in however you need to, okay? Well, here's an example that we're going to do. We want to maximize our conversion of this reaction and also keep another property called activity within a target range. So we have three factors that we're going to study: time, temperature, and catalyst. And the goal here is to get to at least 80% conversion. And we want this activity property to be 63, but we don't want it to go outside the range of 60 to 66. Okay, so let's see how we set this up. All right, so there's the goal: conversion greater than 80, and we want a target activity of 63 plus or minus 3. Okay, so let's see how we do this. Let me get to the right one. So we are going now below in this left-hand side. We're going to pick underneath response surface designs. We are going to pick the central composite design. Okay, so that's probably the most common response surface design that's used, although box banking is another good option and custom for certain purposes. But anyway, this is probably the most commonly understood response surface design. We have 3 numeric factors in this case. So we have the time, temperature, and catalyst. And as before, we would just key in the information with the low and high ranges for the factorial part of the design. The alpha points, it's going to make a recommendation for where those star points need to be relative to the factorials. So for example, time, it's going to move those out a little bit. It'll go 36.5 to 53.4. So it'll put those axial points, those star points, a little bit outside the faces of the cube. There are some options here that with a little more time we'd explore of what one could do here. But for the sake of being brief, we'll just accept all the defaults in this example and move ahead. So I'll hit next. I have 2 properties of interest, the conversion and activity. I'll finish the design, and here's my 20-run design to evaluate these 3 factors. And I'll go get my data. This one will be RxN, and there, boom. So now I have 2 responses that I need to analyze. So I'm going to click on the first one. I'll start the analysis. Now this is where things look a little different than in factorial, because these optimization experiments, these RSMs, are designed for a little bit different purpose. We're not trying to find the factors of significance, but rather we're trying to build an effective predictive equation to use. And in this case, it's suggesting that we would want to use a quadratic model. So we'll accept the defaults and go ahead and do that. So I'll click on the model. Here are the terms that will be included in that model. I'll go ahead and look at the ANOVA. And here we have a significant model. We like that. Because we did replicates of that center point, we did the center point more than one time, we're able to look at whether or not the model fits the data very well. That gets into a lack of fit test. Again, beyond the scope of what we can cover thoroughly today, but because we did replicates, we can do this lack of fit, and not significant is the desirable condition. So to have not significant lack of fit, we have a pretty good understanding that the model we chose, that we created using the terms above, we feel that that will now fit the data and give us adequate predictions. And the fit statistics over here, you know, the high R squareds, including the predicted R squared of 0.75, okay? Always want to take a peek at the diagnostics. So this is looking pretty good. I have this one little data point that's not quite on the line. So if I wanted to highlight that one to see where it appears in other graphs. So let me just kind of zoom in on these a little bit. So here I see that one data point, it's not outside the red lines, so it's probably not causing me any great problems. I could look at the predicted versus actual, and that data point is probably a little bit further from the line than the rest, so you know that's interesting. And if I was really concerned about that data point, there are a couple of influence charts that I might take a look at. One would be Cook's distance, and that one's really buried down with all the other ones, nowhere close to the red lines, so I'm not terribly concerned with that one. And then I can also look at this one called diffits, difference in fits. So what this is each individual data point, if I excluded it from the analysis, does it make a difference? Okay, and what we see here is that particular data point, whether I include it or exclude it, it doesn't fall outside the guidelines. And so even if that data point were a little bit off, it's not doing any damage to my analysis, or nothing material. So I'm not going to worry about it. Okay, so we're happy enough there. Then we need to analyze activity. So I'll start the analysis. This one says that just a simple linear fit will be adequate. So we click on the model, we click on the ANOVA, right? Everything is good here. We have a statistically significant model. we have a not significant lack of fit. Temperature is kind of an interesting one. That is a very high p-value. It's way above the 0.05. And arguably, you could take that out of the model, something called model reduction, and it might actually improve the model by doing so. And we're going to see that in the third example, but I might actually choose to come back here and remove temperature from the analysis. Okay, I still have a very good model, and actually, ever so slightly, I have improved the predicted R-squared. So I've made an improvement by taking a term out of the model. So I'll go ahead, I'll just keep it that way. We look at the diagnostics, that's okay. So now what we want to do is we want to find the optimal conditions. We want to satisfy two criteria. So how am I going to do that? Well, I'm going to go down here into the optimization module, and I will click on numerical optimization. I will look at conversion. And what do I want to do with that? Well, I want to maximize it. So I'll come down here and do that. And the input that I was given is I want to achieve at least 80%. And if I can get as high as 100%, well, I'd like that. I'm not extrapolating because I'm still looking within my design space. But if there was a point in between points that I actually ran that was actually better, I'd want to see it. So, okay, so I'm going to let it pursue. And the little graphic down at the bottom says I won't see any solutions less than 80, but I'm going to see, it's going to emphasize solutions that bring me closer to 100%. Activity, I have a very specific goal in mind for that one. That's going to be target. And we said we like the number 63, but we don't want anything below 60, and we don't want anything above 66. So this little ramp view down at the bottom kind of shows what we set up here, right? We like 63, but it's got to be between 60 and 66. Well, then we hit solutions. And when we hit solutions, here we go. We have this time, temperature, and catalyst load, which will give us a conversion of 91%. And it'll give us the activity that right at 63 that we wanted, right? So it's trying to balance those two goals, one against the other, and this is the solution that it recommends. Okay. Now we can also, let me just show you another little thing here. We can look at graphical optimization, and I'm just going to do this real quickly. I'm going to show you this one. I'm going to hit the graph here. And then the most interesting one just happens to be the AC one, right? So I'm looking at A and C, and I have this yellow region, and I have my ideal solution kind of planted in the middle of that space. But this kind of gives me a way to look at how robust my solution is. Okay, so if I ran less time, for example, I could go all the way over here to the left, and eventually I would go below the activity level of 60. Right? If I went down, eventually I would go below a conversion of 80, etc. Right? So, but anywhere within this yellow region, I would at least be above 80% on the conversion and be between 60 and 66 on the activity. Okay, so that kind of gives you an idea of how big that sweet spot is. Do you have to hit a very small target, or do you have some flexibility? Okay, so that's that example. So the summary here is RSM designs are useful when we have curvature or nonlinearity within the design space, right? Whether we have a hill or a valley to pursue in the interior of the design. It's helpful for optimization. The model terms include quadratic or even higher order terms, in addition to main effects and interaction terms. The downside is that RSMs require more runs, right? You're trying to get more information, and therefore you're going to need more data. And you can use numerical and graphical optimization tools to find the optimal conditions. Okay. Now, if this is the type of thing that you find yourself doing or have more interest in this, of course, there's training that's available that goes beyond what we can accomplish in a 1-hour webinar. So modern DOE for process optimization would cover the kinds of things that we just talked about in greater detail. And for individuals, right, we can offer public courses, but if you have 6 or more, we can create a custom class for you at your company if that's of interest, right? So you can contact workshops@staties.com if you're interested in pursuing that a little bit further. Okay. There's also distance learning options available. So in-person training, although COVID has that, we're all struggling with that, but there is distance learning options available as well. All right, so mixture now. Mixture is a little bit of a special case of a response surface design. So let's see what that does to us. So when we have a mixture, I mean, obviously the factors now are ingredients of a mixture or a formulation. And the response, if you think about it, the response is actually driven by the proportions, right? It's ingredient A versus ingredient B or compared to ingredient that drives the response itself. It's not the absolute amount. And I think a good way to look at this would be this little lemonade example that we always use. So if we're going to make lemonade from sugar water and lemons, and we're going to use a factorial design, well, here's what we would do. We would study everything at its low and high level in combination with everything else. So in the lower left, we would have, you know, a 1-to-1 ratio. In the lower right, we would have 2 lemons to 1 glass of sugar water. The upper left, 1 lemon to 2 glasses. Upper right, 2 to 2. But the problem we have here is the lower left and the upper right are actually the same formulation. It's the same run. It's just that I have more lemonade, okay? And that clouds the math. So the factorial, the math we use to calculate effects and interactions with factorial designs breaks down because of this constraint that we have in the mixture world. So we have custom designs created for mixtures. And for example, if you're doing a factorial with 3 factors, you'd be free to change each factor independently. You could go anywhere within this cube. Your choice of one factor has no bearing on your choice of another. But with mixtures now, if I tell you how much B and C is in the system, well, we can back calculate how much A, right? Because it's going to be 100% less the other 2. So we lose a dimension in the design space. And so if I have 3 components in a mixture, I have a flat triangle that's my design space instead of this entire cube. Okay, so we have to, the bottom line is we have to treat it differently in order to work with mixtures. Okay, so we're going to use an optimal or a custom design here because what we're going to do, we're going to look at a mixture amount type design. So let's think about this. So let's think about medicine. So the effectiveness of a medicine, right? So every once in a while I get a headache. So Excedrin has what does it have? Acetaminophen, it has aspirin, and it has caffeine in it, right? So I have 3 ingredients in the mixture, and I have a choice between 1 and 2 tablets. Okay, so the effectiveness of the medicine not only has to do with the composition, the ratio of the 3 ingredients, it has to do with whether I take 1 or 2 tablets. It's mixture plus amount. Okay, so what we're going to do is we're going to look at a little experiment. That the design space now kind of looks like this prism. The 3 components of the mixture forms these triangles, and then we have the amount factor, which is the dimension that, you know, completes the prism shape. Okay. So here's what we're going to do. We're going to make an ibuprofen coating to make a timed release ibuprofen capsule. So what we're doing is we have 3 elastomeric materials, latex materials. We'll just call them EA, MMA, and TEC. And we're going to explore those in the given ranges, 7 to 20, you know, 7 to 24 to 14. And those 3 ingredients comprise 31% of the mixture. The other 69% being held constant is not changing at all. That might be water and surfactants, whatever, but that's being held constant. So we're only changing 31% of the formulation. right? And then the sum of those three ingredients needs to equal 31%. We are also going to choose how much of this latex coating we are going to use in this laboratory coating system. And we can let that go between 15 and 25 mLs injected into the laboratory coater. And we want to evaluate the drug release at 1 hour and 12 hours, cumulative release. Okay, so let's see how we do this. So let's open up our last example for the day. Okay, so we're going all the way to the bottom of the list now. These custom designs, optimal combined. We have 3 mixture components. We have 1 numeric factor, the amount. I will click next. Here's the 31% that my 3 materials need to sum to. We have the different ranges input for the mixture. We accept that. The coating now, the process factor in mLs, we're going to let that go from 15 to 25. So I'll hit next. Here's a recommended design, 28 runs. And we'll go ahead and put the 2 different responses in. It's how much is dissolved, the cumulative amount dissolved after 1 hour and the cumulative amount dissolved after 12 hours. And we'll finish the design. And there it is. I will get the data. This one's ibuprofen. And we have our data. Okay, then we have to do just what we did before, analyze each of my 2 responses. So I come over here underneath analysis, click on that. I will start the analysis. And here things look a little more complicated than they did before. It's still a response surface type design, but it's customized for a mixture. And here the mixture order is going to be quadratic, but the process order is linear. That's the recommended approach. But we'll just go ahead and say okay to that. Now with these complicated designs, we almost always have terms that probably should come out of the design. So I'm just going to very quickly show you that what I would do is come into auto select, and I typically use AICC backward as the criterion and selection approach, and I will hit start, and it's going to remove some terms from the model, things that are just chasing noise that don't really need to be in the model. So I'll accept that, and you saw some of the terms disappear. Then I will click ANOVA, and it says, well, some of those terms I just got back, it really wants to put, I got rid of, it wants to put back. I always say yes to that question to support hierarchy. And then here's the resulting model. Okay, so we have, fairly complicated model. It is statistically significant. Lack of fit is not significant. That's a good thing. And my fit statistics look good. Take a quick peek at the diagnostics. I'm happy with that. And we could look at the, contour plot, if you will. Let's see. I wanted to look at the 3D just to kind of show you kind of what happens here. So you've got a 3D plot. You can see that it fits some curvature and the coating amount. It's a linear fit for that. So that just kind of moves that curve. Well, you can see what it's doing. Okay. Well, let's go to the 12-hour and do the same thing. So just quickly run through the same steps, quadratic by linear. Actually, it likes this thing called the KCV model. That's a longer story, but that's, we'll just accept the defaults, and it says KCV, it likes that. I will get rid of terms that don't need to be there. So I will click that, click on ANOVA, and here we have the model created. Okay, good fit statistics, significant model, not significant, lack of fit. We'll look at the diagnostics. That all looks good. Take a peek at the model graphics if we want to. But now here's where the magic happens. Now that we have 2 models that were created for each of the responses, the next step now is to find the solution. So how do we do that? Well, we're going to go back to our numeric optimization. We're going to come back to dissolve in 1 hour, and we're going to target that one. We want to see that be 20. That was the goal. But we don't want anything below 10 or above 30, right? So we prefer 20, but we'll look at solutions between 10 and 30. And for the 12-hour, where we'll target that one, we want to see 90, but we don't want to see anything less than 80 or obviously above 100. Okay, so that's the goal there. And then we hit solutions, and there you go. So now we have a formulation, roughly 14% A, 13% B, and 4% C, with about 18 milliliters of coating, and that'll give us a timed release profile where we have roughly 25% released in 1 hour and roughly 87% after 12 hours. So we're able to customize our coating amount and formulation to hit the goals that we set for ourselves. Okay. All right, so mixtures have a built-in constraint that the formulation has to sum to a total. Mixtures are RSM type designs, but they're customized to deal with this constraint. And you can create optimal or custom designs using mixture or 2 different mixtures, like cake and frosting, for example, and all kinds of different design options in this optimal custom world that you can explore. Okay. So if mixture or formulation type work is your forte or area of interest, we also have a mixture design for optimal formulation course. In the same story that I went through earlier, if you have 6 or more, we can customize a class for your group. We have distance learning approaches, and we're looking at reintroducing in-person training. So that's all coming together. And if you have additional interest there, workshops at staties.com. So in summary, a DOE is a planned multi-factor approach to effectively and efficiently determine cause and effect relationships. The statistics in DOE provide the power and credibility to the conclusions. And Design Expert is specialized for DOE and provides a wide variety of design types and modeling tools to address virtually all experimental needs. So there are books that are available written by folks from Staties. So DOE Simplified covers a lot of the factorial type work. RSM obviously handles RSMs. And then the newest one is the Formulation Simplified to get into the mixture designs a bit more completely. You can find case studies on our website, staties.com. So feel free to browse that for additional information. You can find information on statistics made easy by Staties on YouTube. There are white papers and other publications on our website as well. Within the software, you can click the light bulb for screen tips and context-sensitive help. You can email stathelp@staties.com for additional information and help. If you do have a software license, please go under help on the software and copy your license and send that along with your question to stathelp@staties.com. If you don't have a software license, still ask your question, but we'd like to know who you are if you do have a license as well. All right, 11:59 on my time, so we're 1 hour in, so make the most of every experiment. So that wraps up our introduction for new users. We've covered a lot of territory in 1 hour. Probably some of that went a little past you because we went so quickly. But please feel free to seek out additional help or additional training, and we look forward to helping you along your DOE journey in the future. So thanks for your attention. I will leave the question box open for a couple of minutes if there are other questions that you would like to ask while Sherry is on the line.